A Tale of Two Cities. City 1 has a population of 2 million. Nearby is City 2, with a larger population. On the first day of the month, one person infected with a contagious virus arrives at City 1. On the same day, 2 infected people arrive in City 2. The virus takes 21 days to heal and the infected person requires 1 packet of medicine each day. On each day, the virus transmits from one person with the virus to another without the virus. The mayor of City 1 says, "Don't worry. We have 1 million in packets and only 1 patient. New supply comes after 21 days. Is there enough medicine to last 21 days? How much medicine is needed for 21 days? Let's keep track of number of days and number of patients with the virus. On day 1 we have 1 patient. On day 2 we have 1 plus 1 is equal to 2 patients. On day 3 we have 2 plus 2 is equal to 4 patients. On day 4 we have 4 plus 4 is equal to 8 patients. On day 5 we have 8 plus 8 is equal to 16 patients. Notice we are doubling on every step. On day 11 we reach 1,000 infected. On day 15 we have more than 16,000 infected. On day 20 we reach 500,000 infected. We will see that we have used up all the medicines by this day. On day 21 we reach 1 million infected. To the mayor's surprise, on day 21 we have more than 1 million people infected. The number of infected people form a geometric sequence with common ratio 2. Such sequences, with common ratio greater than 1, grow very fast. The 21st term in the sequence would be greater than the 2 million population of the city. The 34th term would be greater than 8 billion more than the population of the Earth. Let's sum the sequence to know how many medicines are needed to last 21 days, till the next shipment can arrive. On day 0, we have number of infections 1. This is same as 2 power 0. On day 2, we have number of infections 2. This is same as 2 power 1. On day 4, we have number of infections 4. This is same as 2 power 2. On day 6, we have number of infections 8. This is same as 2 power 3. And so on. On day 40, we have number of infections 1048576. This is same as 2 power 20. To compute the sum of infections in City 1, it helps to look at what may happen in City 2. This is a tale of 2 cities after all. City 2 has 2 infections on day 1, which is the same as 2 power 1. City 2 has 4 infections on day 2, which is the same as 2 power 2. City 2 has 8 infections on day 3, which is the same as 2 power 3. City 2 has 16 infections on day 4, which is the same as 2 power 4. City 2 has 2097152 infections on day 21, which is the same as 2 power 21. Notice that on each day City 2 has twice the number of infected people as City 1. This means that the sum for City 2 must be twice as that for City 1. This observation is key to solving the sum. But the series for City 2 seems to have a lot of the same terms that City 1 has. What terms does the series for City 2 have that the series for City 1 does not? And what terms are unique to the series for City 1? When we shift the series for City 2, it is clear that 2 has all terms for City 1, except the first one, and City 2 has an additional term, the number of infections on the 21st day for City 2. The sum of the series for City 2 equals sum of the series for City 1 plus last term in series for City 2 minus first term for City 1. Put that together with the sum of the series for City 2 equals 2 times that of the series for City 1. And we see that sum for series 1 is equal to 2 power 21 minus 1 or 2,097,151. When the mayor realized there's not enough medicine for 3 weeks, he wondered aloud if we had more than 21 test kits we could test the population and quarantine the infected person. Luckily, the town had a mathematician. She said not to worry, this is a very sensitive test and 21 test kits is enough. Here's my plan. First, collect blood samples from all 2 million residents. For test 1, we combine a part of the samples of half the population, 1 million, and test the combined sample. If the test is positive, we know the person is one of the million that is tested. If negative, we know the infected is one of the untested 1 million. In either case, after one test we have narrowed our search from 2 million to 1 million people. For test 2, we have the search from 1 million people by combining 500,000 samples and testing while leaving 500,000 untested. If positive, we have narrowed our search to one of 500,000 that were tested. Else, we know the infected is one of the 500,000 who were not tested. Notice that with each test, we are having our potential candidates for the infected person. After test 7, we have narrowed our search for the infected person to be one of 15,625. After test 10, we have narrowed our search for the infected person to be one of 1954. After test 15, we have narrowed our search for the infected person to be one of 62. After test 20, we have narrowed our search for the infected person to be one of 2. For test 21, we have only 2 candidates left. We test one and if positive we know the infected person. Else, the infected person is the person who was not tested. Key learnings. 1. Geometric sequences, as we saw with infections, with common ratio greater than 1, can grow very fast. 2. Geometric sequences, as we saw with number of patients to test, with absolute value of common ratio less than 1, can go to 0 very fast. 3. To sum a geometric series, we constructed a second series with same common ratio, but with first term equal to the second term of the original series. Then we took the difference of the two series to help obtain the sum. 4. For our example, day n in city 1 had 2 power n-1 infections. In general, term n of a geometric series is the first term multiplied by the common ratio to the power n-1.